So I've been instructed to stand here so that I can appear on the film at least once. I want to give one thing, an acknowledgement. I am going to use some simulations which are real. That is, they are actual calculations of quantum mechanics in action. And I owe a debt of gratitude to the physicists or computer scientists at the University of Colorado. So without further ado, then let's begin. I can figure out how to use this thing. There we go. So I want to talk about, first of all, something simple, physics words. What does the word quantum mean? Well, quantum comes from the word Latin quantus, and we get our words such as quantity, quantify, quantitative from that word. And in physics, we use this as an example that the energies of electrons in atoms are discrete. I'll explain that later what that word means, discrete. It means they can't be any value, they're definite values. We say in physics that it's quantized, the energy, not continuous. You'll hear more about that as time goes on. I use the word quantum physics in my title here, and not the more conventional words that physicists use, mechanics, because I didn't want you to think of automobile repair. So mechanics in physics is the branch of physics dealing with motion and forces that produce that motion. So the moon around the Earth or the ball hit off the bat of a baseball and so on would come under that. And in quantum, we use the word quantum mechanics or quantum physics, as you'll hear, to describe the motion, say, of an electron around the atomic nucleus. So quantum physics is really, without a doubt, one of humanity's greatest scientific achievements. It ranks up there, you could probably think of many things, along with Einstein's theory of relativity. I got the next word in my mouth there ahead of time. And Darwin's theory of evolution and discoveries of things like DNA. So if I use the QP, you'll know it stands for quantum physics. It has led to the understanding of virtually all of chemistry, materials, biology, and medicine. Electronics, this device, the computers that you use, the cell phones, would have been impossible without an understanding of this piece of physics. Television, the GPS system we use to navigate, nuclear power, the internet, medical diagnostics such as X-rays, CAT scans, MRI, lasers. I could go on for a long time. You get the idea. It's really an enormous achievement. So what we're going to talk about tonight is a few things. What is the nature of light and other subatomic particles? Is it wave or particle or neither? Okay, we have to adjust the mic. Should I talk louder or softer? Talk louder. I have a soft voice. We'll take a look at what do atoms really look like. And I'm not going to probably have time for the uncertainty principle because I want to talk about something else. But if you ask me a question, I'll try to explain that a little bit about it. We'll also meet some of the scientists involved in creating this new understanding of nature. I won't talk about important things you may have heard about, such as the Pauli exclusion principle, which explains why matter is hard, why you can't put your hand through a table. Quantum tunneling, particles going through walls. Quantum cryptography, sending messages in code. Quantum computing, I will just mention that a little bit, but that's something that is on the horizon. I won't be talking about the devices such as lasers and transistors and so on. So, a little historical perspective. While this great work was going on, this is what your hometown looked like, just to give you a feeling for the era in which this was taking place. Okay, this was Hotel St. Francis around the time of 1920 or so. We'll return to this time and you'll see what else was going on around then. So before we talk about quantum objects, I want to make sure that you have a good understanding of how ordinary objects behave, so you can contrast that with how quantum objects behave. So, as you know, baseballs and planets follow a very predictable path. There are known forces such as gravity and the laws of motion. So if we repeatedly do something, like throw a ball at a wall or throw this ball up in the air, it's a little dark but you can't see it, the same way, it'll always come back the same way. Now you may not think that's important, but think about this. If you play basketball, or you play baseball, you play any sport, what makes that possible? What makes it possible is that when I throw the ball up a certain way, I've developed the ability to catch it because the ball executes a repeatable path if I throw it the same way every time. Now, that means that the air currents have to be the same. If I'm a baseball pitching the ball, I have to throw it with the same spin. The batter hitting the ball would have to swing with the same speed. If all that occurred, the ball would go exactly the same place every time. At least exact enough so that any fielder or person playing tennis would be able to retrieve it with a little practice. That reproducibility, that behavior is in what we call classical physics. There's another important point. The ball can go at any speed. Or you can drive a car, if you wish, at 20 miles an hour, or 21 miles an hour, or 75 or 73. You pick 73.124 miles per hour. Classical objects can basically, for all practical purposes, go at any speed, and their trajectories are smooth and predictable. So what about very small particles like an electron? Well, subatomic particles behave unpredictably. We can't know their paths with certainty. We can only say where they would probably go. And by the end of this talk, I hope you're very familiar with that concept. So, unlike this ball, if we kick an electron the same way every time, sometimes it might go to the left, sometimes to the right, sometimes straight ahead. There is no way to predict exactly where a given electron would go, even though we give it the same force in exactly the same way every time. But, as you will see, if we look at many such electrons, we will see a definite pattern. And that's a distinction between the classical world and the quantum world. We can only work in where it probably would go. A subatomic particle is also never just here or there, but seems to be in many different places at the same time. That's something that is new. Everybody would agree that this ball is right here in my hand. There's no disagreement about that. But as we'll see, that's not necessarily the case in quantum physics. So this behavior of unpredictableness and being in seemingly, we'll describe that in more detail, in at least having the probability of being different places at the same time, is the behavior governed by quantum physics, where randomness and probability rule. Now, what do we mean by probability? All right? Here's a simple. What it means is, what are the odds? Okay, what are the odds of something happening? So, simple example, we flip a coin. What is the probability of getting heads? What's the probability of getting heads if I flip a coin? 50%. Very good. It's 50%. What about getting tails? No fair reading. 50%. Okay, it's 50-50, right? If it's a fair coin. Same way if we throw a die, what's the probability of getting a 5? Well, there are 6 sides to the die. If it's a fair die, it's 1 out of 6, which works out to be about 17%. So that's what we mean by probability. Now, let's take a little experiment here that we're going to do. We have a little wall here, and I have 2 holes drilled in the wall, which are called slits here. And I'm going to take a BB gun, and I'm going to fire BBs at this wall, sort of randomly across this space. So I'm going to ask, what is the probability that BBs will hit the screen in the middle? Well, the picture tells the story, right? If I had to ask you, most of you would say, well, yeah, I mean, I expect I'd get a pile of hits right behind this slit, and I'd get a pile of hits behind this slit. But a BB to go over here would have to scatter off this wall and come over here. It's very, not so much likely, especially if I make the walls extremely thin so it can't scatter very easily. Most of them are going to more or less wind up back here, especially if I move the gun way back here and shot straight ahead like that. So they more or less went right through. Everybody in agreement about that? Okay. So now, I'm going to ask, we're going to start our exploration of quantum physics with a basic question. What is light? Anybody got an idea what light is? Yes, back here.
Energized particles.
Energized particles. Somebody else?
Waves.
Waves. Very good. So we have one answer that says it's particles and one answer that says it's waves. Let's do an experiment in our mind. We're going to shoot the light at the slits, but first I want to tell you what one of the most brilliant mathematical physicists ever to have lived, Isaac Newton, thought about this. Newton lived around this period of time. He lived to be about 84 years. By the way, here's his picture. He was born the year Galileo died on Christmas Day in England. Now, Mr. Newton thought that light consisted of what he called, back in that day, corpuscles. We would call them particles today. Okay, this was around 1700. Now, what's special about a particle? Well, this is a big particle. It's localized in space, right? It's right here. So particles are localized in space. They can collide with other particles, or they can collide with a wall if I threw it up there. And for those of you who are taking a little bit of physics, in such a collision, energy is conserved. This happens to be the kinetic energy. Don't worry about that if you're not interested, but I thought I'd write it down. And the momentum is conserved, which is the mass times the velocity. So this is the way particles behave. Particularly, they're localized. So, okay. Now, jumping ahead of more than about 150 years, there was a man, physicist had done many experiments, a man named Maxwell, who was from Scotland. And one of the things I want you to notice about doing physics and doing science, it's really international. So we're going to see lots of people from all over the different world who've contributed to this. So Mr. Maxwell was from Scotland, and it was by now pretty much well established that people have kind of forgotten about Newton's picture of light being corpuscles or particles, that light was a wave because light reflects. Here's how light, it'll reflect off a surface, or it can do something we call refraction and bend in going through a pane of glass. That's why a pencil looks, if you put it in water, the light is bent coming out. So if light is a wave, it therefore is very unparticle-like in the sense that a wave is extended in space, all right? Unlike a particle, which is localized in space. So, you know, you've all stood at the beach and you've seen waves come in. They're spread out. That's what that means. And it's actually a fundamental thing. Radio waves and things like that, we know, are spread out in space. They're not like particles. And they have a wavelength, a frequency, and an amplitude. So this is a picture, a schematic picture of how light, our understanding of what a light wave looks like. There are in oscillating electric and magnetic fields. You go from the peak to the next peak. That's called the wavelength, the amount of space it takes to reproduce itself. And it fluctuates with a certain frequency back and forth, so it's got a frequency. And the amplitude is going to be small or big, so it has an amplitude. Those are wave-like behaviors. Very different from a particle. So let's do an experiment to decide whether light is a wave or particle. So I already took you through this example of the BBs, BB guns. BBs are definitely particles. No disagreement about that, right? We see two regions of hits. And the one thing that's important is the BBs arrive as whole particles. You never get a fraction of a BB coming through. All right? And the BB will always go through slit 1 or slit 2. So, will light behave the same? Anybody got any ideas? It does not. Very good. Pardon?
We get interference patterns when it goes through two slits.
Okay, wonderful. I love it. when you guys when you know some physics. So let's see what happens. He said that we're going to see what is called an interference pattern, and we're going to exactly see what that looks like right now. And this is an experiment that was actually done by a man from England, Thomas Young, who shot light through slits like this in the early 1800s. And if light were a particle, here's what we'd expect. If we opened up the right slit, now there are two slits here. If we open up the right slit, we should see a pattern of hits behind the right slit. If we open up the left slit, we should see a pattern of hits behind the left slit. If we open up both slits, we should see two bars of light. Everybody agree? If it were particle-like, like the BBs. But what Young actually saw was this, a series of light and dark stripes. Sure doesn't look like a particle. So, what does this mean? It means light behaves like a wave. So imagine that, and we'll show you in detail what this means. Here are the slits. Here's a wave coming in. And out from behind each one of the slits starts a little wavelet. And each little wavelet spreads out in space. And when they overlap constructively, as I'll show you in a minute, you get a light spot. And when they cancel each other out, you get a dark spot. And so you see something like this. Now, here's two water droplets hitting a water. And here is an example of what we call constructive and destructive wave interference. Imagine I have a blue wave and a green wave. When I line them up just perfectly, then the red wave, which is the sum of the two, is bigger. But I could have also slid the green wave over here, like here. And now, when I add them up, the red wave is 0 because they exactly cancel each other out all along here. That's called destructive interference because they have canceled one another out. Okay? Now, let's make this clear. Okay, so here's a faucet dripping in. Everybody can see that. Now I'm going to increase the frequency of the drips. This is real physics, by the way. This is not cartoons. People have actually done calculations to show what happens. So you're seeing now those waves interfering with each other, both constructively in the light regions and destructively in the dark regions. What if we look at, instead of water waves, let's look at sound waves. So there's a loudspeaker. It's booming away. I'm going to make another speaker. I'm going to increase the frequency. So these are sound waves. A sound wave now is vibrating air. And again, you see the same phenomenon of wave interference. And by the way, just to show you what actually it looks like, this is what the air molecules, the atoms in the air actually look like, so that if you, this is not part of quantum physics, but it's kind of fun, if you look at any one of those with an X on it, it isn't moving very far. And you see that there are regions where things are sparse, not many atoms, and regions where they're dense. Okay? That's wave interference. And we can do the same thing with light. So I have a laser going, or a light pulse, and we see the same phenomenon. Now I'm going to put a screen up over here, which is like our screen where the bullets went through. And here you see this striped pattern that Thomas Young saw when the waves are actually brightest right between the two, because it turns out the waves interfere constructively. Right there. And over here, they almost cancel each other out. And over here, they're backlight again, and so on. All right? So that's what wave interference looks like. It's what you'd expect if light were a wave, and in fact, it is. But what about our old friend Isaac Newton? You know, Newton was one of the smartest guys around. And I don't know how he knew this, but he thought light consisted of particles. Particles are localized in space. And I've just shown you that light behaves like a wave, right? So was Newton really wrong? Okay, now comes along a gentleman you've probably heard of in the early part of this century. He was from Germany, Albert Einstein. And Einstein took a look at a series of experiments, which I'm going to take you through rather quickly. And the reason I decided to take you through this, it's called the photoelectric effect. Einstein won the Nobel Prize in Physics, not for relativity, but for this in 1905. And the reason it's important is this is what causes solar power in your solar cells. So here's another example of quantum physics in the real world. So follow me through. If I shine a blue light on this metal down here, what we find is electrons come out. So the light is knocking the electrons out of the metal. So if light is a wave, as we just saw, then as we increase the brightness of the light, the wave should have more energy, right? Go to the ocean. If you get hit by a wave which is, 6 inches high, it's fine. If it's 6 feet high, you're going to get knocked over. The higher the wave, the more energy. So if light behaves like a wave, let's go back, then as I increase the intensity of the light, the wave height should be more energy should hit the electrons, and they should speed up. So I get more electrons out because I've increased the intensity of the light, but if you measure the speed of the electrons, you'd think you'd get more energy. They come out with exactly the same speed. This is not the way a wave should work. A big wave should knock them out faster. Now, if I hit the same metal with a red light, no matter if I make it just as intense as the blue light, nothing comes out. Well, how can that be? I'm still whacking the electrons, right? I've just changed the color of the light. So, what Einstein said, and I'm going to give you a simple example of this if you don't follow everything on this page, so don't worry, that light behaves like a particle, which carries an amount of energy E. This minimum energy, you may have heard the word, is called a photon. It's a light particle called a photon. And your 100-watt light bulb emits about 100 billion photons per second, because Einstein was right, okay? When he said that there were these little light particles. And there's a lot of them. So individual photons hit electrons like particles hitting particles. Here's an electron, photon comes in, knocks the electron out. Now, here's the key point. Blue photons have more energy than red photons, so they hit the electrons harder. That's what Einstein figured out. And the reason that is that the energy, it turns out, depends upon the frequency of the light. Now, this is the electromagnetic spectrum. Here's the visible part. Up at this end, the frequency is higher. Can you understand frequency? The wavelength is smaller. It's oscillating back and forth faster than over here. Frequency is higher at the blue end than at the red end. The electrons, the blue photons have more energy. They knock out the electrons, whereas the red photons in this example have a smaller frequency. They don't have enough energy to knock out the electrons. So here's an example which makes this maybe a little clearer to you. Imagine I have a stadium here, and I have a billion people in the stadium, just in our mind's eye. They all want to get, just in our mind's eye. They all want to get out. These are the electrons, all right? They'd like to get out of here. How are they going to get out of the stadium? Well, it turns out they have to pay a toll. There's a toll booth. The electron has to pay a toll too, by the way. There's a little energy barrier it has to get over. So these people, the toll in this case, whoops, I'm going to go back, is $15. All right? Now, overflies someone like Bill Gates, feels sorry for these people. He starts dropping money, and he drops 1,000 bills of two sizes. And this is blue, and it's 20. It's not showing up too well, I'm sorry. And this is red, and it's $10 and $20. So the bill size corresponds to either red light or blue light. It corresponds to the photon energy of $10 or $20. So what happens? If you pick up a bill down here and you get a blue photon or a $20 bill, you can go through and you pay your toll and you come out over here with $5, okay? That's like the electron being knocked out and comes out with a certain amount of extra energy left over. But if you were unlucky enough to pick up a red photon or a $10 bill, sorry, you can't get out. It's impossible to get out. So this is the analogy with light, and it illustrates the particle nature of light. Now, let's go back to our double-slit experiment, where I shined the light through, and see if we can find any evidence of particles in there. So I've got a laser here. I'm going to put some slits in front of it, and I'm going to turn on the laser here somewhere. It should be going on. And let's see. What's going on here? Well, this is too bad if it doesn't work, because... That's right. Thank you very much. So, I knew it would work, but we needed to have the help of the man in the front row. All right, so here's our gun. We're shining a laser or a photon beam at these two slits, and this is by now what you have seen. Okay? That should be very familiar to you. But now what I want to do is I'm going to shoot one photon at a time at the slit. So we'll put the double slits back. We will turn on the gun, and there he goes. Okay, now I want you to tell me what you see. Anybody? Yes?
So you said that's a single photon?
Yeah, one photon at a time is hitting the slits.
It looks like it's splitting.
Yeah. And it looks like it's splitting, right. What else do you see?
There's light showing up behind no barrier.
Okay.
When it arrives at the screen, it arrives as a particle, as a single event.
Yeah. It seems to be hitting in dots, doesn't it? There was a wave right there, and in fact, let's do it more rapidly. I forgot to hit the rapid button. That's okay. We'll now do it faster. All right? So, what I'm going to do is I'm going to stop it right there. Does that look like a wave passing through? It seems to be spread out in space, not like a particle. It seems to be starting wavelets, just like our sound wave did, and all that sort of thing here. Now, I want somebody to tell me where it's going to hit on the screen. Hold up your hand. Tell me where it's going to hit. Anybody want to make a guess?
Somewhere.
Somewhere is not. To the right, to the left, the middle? On the left. Okay. We're going to test your... excuse me. Okay. Guess? Middle? Can anybody guess? Okay. So what this illustrates that I told you at the very beginning There is no way to predict exactly where an individual particle is going to go in quantum physics. It looks random. You cannot predict it. What you can predict with exquisite precision is the overall pattern, the overall probability. And you're already beginning to see that pattern emerge. There's very few hits here. There's fewer there. We're starting to build up the bright spot right behind. We're starting to build up the bright spots on either side. If I let this run for half an hour, you would see a beautiful interference pattern. Okay? So, randomness, seemingly unpredictableness. Somebody move this, thank you. Those are the lessons of quantum physics. You cannot predict individual behavior like that. So, notice we can see the light interference pattern from two slits with one photon at a time. That's really interesting. It interferes with itself as it goes through the slits. All right? Before the photon hits the screen, it seems to be in two places at once. It seems to be going through both slits at once. Otherwise, we could never get an interference pattern, as we will see. But the individual photon paths are unpredictable, only their overall pattern. The photons, they look like they were waves, and then they suddenly show up like particles on the screen. Now, if it's really a particle, you might say to yourself, which slit did it go through? If you were still back with Newton and Einstein, after all, this ball, we know, is going to go through one slit or the other. So people tried this. And what you see, as you just saw, is that if we, okay, let me back up. Here's my experiment. I'm going to put a detector behind each slit. All right? So when the detectors are off, or when they're not there, as I just showed you, we see interference, this beautiful interference pattern, which can only occur if the particle goes through both slits at once, like a wave. So now, I'm going to put the detectors in place, and what I see is the following. This can only occur if the particle goes through both slits at once, but I never see both detectors firing at once, ever. I always only see one detector or the other one firing. And when one of the detectors fires, I never see interference when either one of them fires. I always see a pattern of hits. If detector 1 fires, going through this slit. If detector 2 fires, I see the hits over here, one or the other, but never this. So, the act of observing which way it went resets the probability wave that produced this to one slit or the other, like a particle. So by observing which way, we have changed it from wave-like to particle-like. Okay. So quantum wave particle behavior. This behavior, where a particle is in a state of indeterminacy, which means it could be either one of those two slits until measured, is typical of quantum physics. Indeterminacy means both here and there until measured, or both through up and down slits. A big particle like a BB does not do this. We have a strong sense, and we know that a BB, a baseball, or the moon is there in a particular place, whether we are looking or not. But as soon as we looked, we changed things in a quantum sense. Now, I happened to notice this cartoon a couple of days ago in New Mexico. I don't know if, whenever I think about it, I always religiously read Dilbert because I have a sense of humor.
How do you observe? What does looking at it mean?
A good question. What does looking at it mean? We actually build, we're not talking about looking at an electron or a photon with our eye in this sense. We have very sensitive detectors that can detect a single photon. And it really works very much like I told you the light comes in, it knocks out electrons, we amplify that and get a little pulse of current, and we have a hit, and we can measure it. Okay? So that's what I saw a couple of days ago. So light summary. Light behaves like a wave, showing interference and spread out in space, and like a particle, hits at a point. The individual particles, however, are unpredictable. Only the overall pattern is predictable. I want to give you another example. These are two pictures taken by me because I like to take pictures of windows, not because of this talk. But I would like to ask you, what do these pictures have in common?
Pictures of neon signs.
Pictures of neon signs. Anything else? What do you see back here? Reflections. What's that? Car. Now, believe it or not, this is quantum physics in action, and it's really kind of interesting. Because all photons of the same color of light are identical. Okay? So here comes one. It hits an object, a star, outside this window pane. It bounces off, heads toward the window pane. A number of things can happen. It can go through the window pane and hit the object behind the window, like the train ride sign or the open sign. Or it could have bounced off the window pane into my eye, and I would see the reflected image of the car or the building behind. When it gets to the window pane coming back out, it can go through or back in again. Now you say, so what? Okay? But I told you every single photon is identical. So why does one decide to go through and the other one decide to bounce off? Remember, you cannot predict the behavior of a single quantum particle. The only thing you can say is that some go through and some bounce off the windows. But if you were to tag any individual one ahead of time, back here, you wouldn't know whether that photon was going to go through or off. The best you could say is maybe 10% are reflected and 90% are transmitted. Okay? So the next time you're out looking at windows, think about quantum physics, because you're observing it in action. The mystery is, of course, they're all identical. How do they decide? Think about that. The same is true of radioactivity, by the way. Some atoms decay fast, some slow, only the overall pattern. All the atoms are identical. Why do some go fast? Why do some go slow? We can just measure a half-life. We can say after a half-life, half of them have decayed. But there's no way of knowing why an individual, and no one on the planet can tell you why. It's a quantum mystery. Okay, what about electrons and other particles? I've talked about light. Our electrons are particles, right? We've all been taught maybe the picture of a carbon atom with electrons going around the nucleus. We'll talk about what that really looks like in a minute. But we tend to think of electrons as particles. And in fact, electrons do behave like a particle. In 1920, a man by the name of Compton, this time an American, again the internationalness of physics, showed that if I have a light particle coming in and striking an electron, he gets a billiard ball collision. So, you have a question?
Well, on the thing before where you said you don't know, no one knows which ones are going to go through and which ones are going to bounce off. Is that just because we haven't discovered it yet?
What we think is that that's the way it is. And, you know, the very famous physicist I'll be talking about in a minute, Richard Feynman, I looked up, he gave a wonderful series of lectures on the web. And what he said is, I'm going to tell you about this, and if you start thinking, how can that be? You're going down the rabbit hole, and you'll never come out again. That's the way it is. That's what it makes quantum physics so interesting and so phenomenally controversial in some sense, and yet it's absolutely correct. So I do not know the answer to that, and I don't think anybody does. So electrons behave like a particle if we scatter a light wave off, just like two particles scattering. And I didn't show you that video. I threw my ball up in the air instead. So what if we do the two-slit experiment with an electron? Well, what do we see? I'm going to just tell you what we see. We see that individual electrons appear at first to hit the screen in a random fashion, like I showed you the light photons did, those dots. We can't predict where any single electron will hit. When we look at many, many hits, though, we see a wave-like interference pattern. And therefore, are the electrons therefore waves? The answer is yes. So these quantum particles have both wave and particle-like behavior. It's strictly not true to say they are a wave or a particle, as we'll see, as I've been saying. They're something else which has wave-like behavior sometimes and particle-like behavior other times. So you could ask the question, well, waves of what? Now, what physicists discovered, and here are two of them, Irving Schrödinger, who was a German, and Max Born, another German, lived roughly around the same time. Schrödinger created a very famous equation, which all physicists use all the time. These are quantum probability waves. They're not like water waves or sound waves. So we associate a probability wave with every particle, electron, proton, neutron, or photon. So these waves here, which maybe showed up as water waves before, are really these probability waves. And what it means is simply that a particle, if we want to use that language, has a higher probability of being where the wave is large, but it can still be anywhere. So you saw that wave going through the two slits. It was spread out. And where the wave was brightest is where we would most likely find the particle. So, quantum wave particle behavior. Matter and light are described by quantum waves, which can extend throughout all of space. The wave can also be localized, but not completely, it turns out. In the two-slit experiment, this probability wave goes through both slits. That's what we saw. It's the probability wave going through. When we measure at the screen, this probability wave or quantum wave collapses to a particular point on the screen, so it hits like a particle. Contrast that with an ocean wave hitting the beach. When the wave comes in, it never hits at one point. It hits all along the beach. Okay? Whereas these quantum waves show up when they finally are detected at a single point. And I'm repeating this because I want you to get these points. Where any given hit occurs seems random. You saw that. It was impossible to predict ahead of time. But averaged over many hits, the pattern corresponds to a wave interference pattern. What Albert Einstein said that I really loved is, quantum physics formulates laws governing crowds, not individuals. He had a wonderful way of putting things sometimes. I just discovered that quote last week. Okay, we're going to shift a little bit, and I'm going to talk about the atom, because I think it's important that you know what an atom really looks like. So, what do atoms really look like? Well, our old picture was kind of like the solar system. I mean, anybody ever see pictures of atoms in books that portray an atom like the solar system? What you have is a nucleus. This is the hydrogen atom, the carbon atom, and a bunch of electrons orbiting around in some kind of orbits, and these are circular orbits. For the carbon atom, there are actually 6 electrons to balance off the positive charge in the nucleus. Carbon has 6 protons in it. That's what makes it carbon. They're positive, so the atom is neutral, so it has to have 6 electrons. So this is the old picture, which is wrong. Electrons are in circular orbits, and in this classical picture, when you think about this, the electrons are negative. How many people knew that? Anybody know that electron is negative? And the proton, positive. Unlike charges, positive and negative, what do? Attract. How can an atom exist? All right? These guys would fly into one another really fast. Goodbye, world. All right? We never have us. It's not a good picture. This is what the electron, quote, orbits really look like in a pictorial fashion. These are supposedly 3D. So these two electrons right here, closest to the carbon nucleus, they sit in an orbit which looks like a fuzzy ball. All right? And right there in the middle is the nucleus. Now, by the way, if the nucleus is the size of a baseball, the nearest electron is 5 miles away. Okay? So those electrons are spread out over, in that example, 5 miles, but in a real atom, they're very small. So the electron exists in a probability cloud or probability wave, what I just told you. All right? Where the wave is darkest is where the electron is most likely to be. It's darkest in the middle because it likes to cuddle up to this positive charge. But it's still spread out. Okay? Now, I put in the next electrons, and these electrons here, of which there are 4, don't really fit into the same orbit. The first 2 go into something that looks like this. It looks like the same fuzzy cloud, and then there's very little electron probability, and then it sticks out around here. This is like an inner tube. This is a 3D thing. So it's like a ball surrounded by an inner tube. That's what the electron orbit looks like. Now, I put the next 2 electrons in. All right? They fit into an orbit that looks like this. It looks like a dumbbell. Again, the carbon nucleus is in the middle. This dumbbell can point in 3 different ways. And that's what the electron orbits really look like in quantum physics. They're probability waves. Notice that the wave, the electron, has a probability of being anywhere in here. That's what I told you. It can be in different places, so to speak. It's most likely to be found here, where it's darkest, but sometimes it can be out here. So they're spread over 3D clouds. And the other thing about the electrons, of course, they go around in certain speeds. And we physicists make graphs of here's the lowest speed, the lowest energy electron. That's the first 2 electrons that I put in, that I told you with carbon. The next 2 have a higher energy, they're moving faster. The next 2 higher. The energy is going up here, that's all that means. This is the number of electrons I can put in each of these orbits. Now, I told you at the beginning about this word quantized. And notice, the electron can be here, and I move up in energy, and this is no man's land, or no woman's land, no electron's land. No electron can have this energy, okay? It's like a car that can only go 1, 10, 15, or 20 miles per hour. It cannot go 11 miles an hour. It cannot go 5 miles an hour. It can go 1 mile an hour, or jump up to 10, or jump up to 15, but nowhere in between. That's what we mean by quantized. The energies are quantized. They can only go at certain speeds. Now, how many people recognize what this is? Periodic table of the elements. Somebody's got to know this. I know Einstein knows it. So here they are. Hydrogen, helium, lithium, beryllium, there's carbon. So what quantum mechanics or quantum physics explains is how this thing got to be organized like this exactly. And it's pretty simple in a certain sense. We can put 2 electrons in this level. The first one that goes in is corresponding to hydrogen. The next one that goes in corresponds to helium. Then we can put another one in, we get lithium. Another one in, we get beryllium. By the way, I'm changing the number of protons in the nucleus as I go along here. And then finally 2 more. One more makes boron and carbon. So quantum physics just explains, because of the systematic filling of these energy levels, how we get the distinct elements. Why is carbon different than nitrogen and so on? Okay, one more thing about the atom, which is really kind of cool. I can put 2 electrons up here. And remember, electrons up here. And remember, this is what they look like in their probability clouds. if there's an open space down here, these electrons can jump down. So this probability cloud jumps from this shape to this shape. It changes its speed from up here to down here, but it never goes in between. It literally goes from here to there without going in between. So a normal classical thing like a BB or ball cannot do this. If I want to go from here to there, I have to move the ball continuously from here to here. I cannot just show it to you here and then suddenly have it appear over here. But an electron in an atom can do that. Okay, now I'm going to stop showing you view graphs, and I'd like you to turn up the lights, because I want to have a couple of volunteers. Because if you turn on the lights, I have 2 volunteers who are willing to do a little bit of acting with me. And if you don't volunteer, okay, come on. 2 guys, any girls? Huh? Okay, it's the guys' turn today. So I want you guys to stand right about here. All right, that's great. Now, how about standing like this? One like this and one like this. There's a reason for this. You'll get the idea in a minute.
Back to back.
No, not back to back, facing each other. All right. Now, I want you, the only criteria that in choosing you is that I know you guys will do what I say, right?
Correct.
Okay. So I've got something over here. I'm going to take it up and bring it over here. I've got a box. You didn't see this. I had it behind the podium. And what I want to hand you this box, okay? I want each of you to put your hands under each end of the box and hold it for me so I don't have to hold this heavy box. Okay? You ready? You got it?
Yeah.
Okay. I can take my hand away? Okay. Great. Now, whatever you do, don't drop the box. Okay? Now, how many people, what I didn't tell you is I put an object in the box before this. So if you guys could just kind of shake the box around a little bit to randomize the position of the object. Okay, that's good, that's good, that's good. Now, how many people have seen the magic act where the beautiful woman is cut in half by the magician? Anybody ever seen a magic act like that? Okay. So, actually in my back pocket here, I happen to have a thing I'm going to slide into the box, and I'm going to put it right in the middle. You guys ready? Don't drop the box now, okay? Because this thing is heavy. You ready?
Ready. Oh my.
Okay.
Oh my.
Now, the box has now been divided into 2. If you guys could step back just a little bit, each one of you has half of the box now. Don't drop it, okay? Okay. All right. Now, what I would like you guys to do is I want one of you to go over there to San Francisco. Carry your box. Now, before you go, and I want the other one to go over there to New York. All right? Now, there's only a couple of criteria that I ask you to obey while you're doing this. 1, don't drop the boxes. 2, don't let anybody else touch or otherwise interfere with the boxes. And 3, don't look in the box until I tell you. Okay? All right. San Francisco, please. New York, go over there. All right. Now, I'm going to tell you what I put in the box now, and then I'm going to ask you a question. I put a 50-cent piece in the box. Now, my question to you is, you guys all saw what happened, right? Is the 50-cent piece in New York or San Francisco? And if you are not sure, tell me what you do know about where the 50-cent piece is. Yes, sir.
The 50-cent piece is in both New York and San Francisco until you look in the boxes.
No. It's a very important point. But okay. Anybody else? Yes, sir.
It's half in San Francisco and half in New York.
This is a 50-cent piece. Let's not get carried away. It's like this ball here. There's a reason we're starting off with a 50-cent piece.
Can you repeat the answers, please?
Repeat the answers. He said that it is 50% in San Francisco and 50% in New York. How many people have sent a loved one on a plane to New York? Would anyone here say that they were 50% here in Santa Fe and 50% in New York? Okay. Yes?
You don't know whether it's in New York or San Francisco until you look in the boxes.
Right. We don't know whether it's in New York or San Francisco until we look in the boxes, but don't look in the box yet. And because it's a 50% piece, we know for sure that it's either in New York or San Francisco because I'm an honest guy. Okay, I told you I put it in. We shook up the box. It's a real classical object. It's either in New York or San Francisco. What's the probability of being in New York? 50%. San Francisco? Okay. I told you I was an honest guy, but I lied to you. I didn't put a 50-cent piece in the box. I put an electron in the box, and we're getting ready for the young man's answer back here. The electron is a quantum particle. Now, where is the electron? I'm going to ask you again. You, sir. No, the first person who answered. Yes.
It's in both New York and San Francisco until you open the box.
Okay. So what we would say, a little more precisely, and the language is important here. The math is infallible. We're not doing math. But the language is that the electron quantum state is in a mixture of being in New York and San Francisco at the same time with equal probabilities. Okay? The electron state is in a mixture. You can't do that with balls or quarters. They're either one place or the other for sure. The electron state is in a mixture. Now, look at the box. What do you see? Do you see an electron or do you not see an electron?
I don't see it.
Okay. Now what do we know? We know with 100% probability that the electron is not in New York. It's in San Francisco. Just prior to him looking in the box, which is what this gentleman said back here, it was in a mixture. And what happened is, instantaneously across space, the mixture, even though we haven't looked in the San Francisco box, changed from having a 50% probability of being in San Francisco to 100% probability because we looked in New York. Okay? A quantum mystery. And that illustrates.
Some would say it was always the same.
There is an interpretation. What I gave you is the classical interpretation of quantum mechanics. And the exact statement is that the quantum state is a mixture of both possibilities. The state collapses to one of the possibilities, becomes 100%, and the other 0% when you look at it. Richard Feynman actually invented a theory where the electron went both possibilities exist. It went to New York and it went to San Francisco, and when you looked in the box, you just found out which one. That's another interpretation, okay? Okay, thank you very much, guys. I appreciate it. Now, this is the object in a box. And I don't have time to go through this, but there was a decades-long argument between Niels Bohr, a Danish physicist, and Albert Einstein, a German, about what we've just been talking about. Einstein, had a real difficulty in believing that quantum particles couldn't have definite properties. The quarter or the 50-cent piece, you knew ahead of time it either definitely was in New York or was definitely in San Francisco. Okay? And Einstein had a real problem with that. What Niels Bohr said is, before you look in the box, you really don't have any right to say anything, except, you know, that there's an equal probability. This was a raging argument for a long time. Now, I don't have time to talk about this, but this is not just, you know, we did this experiment here in our mind's eye. But this has real implications because people right now are building quantum computers. They have built them, they're working, and they have the possibility, as time goes on, there's a lot of technological things that have to be overcome, and the mathematical methods have to be developed, but there's a real possibility that quantum computers could solve certain kinds of problems in an hour that might take, you know, 1,000 years using conventional computers. And the reason is that a quantum object, you know, inside of a computer, I don't know if you know this, but the basic element of a computer we call a bit, it's a switch that can either be on or off. Okay? You can represent any number, like the number 4, with so-called binary system of numbers, 0 and 1. We have a decimal system. We count from 1 to 10. Okay, when we write 100, I mean 1 in the hundreds column, 0 in the tens column, 0 in the ones column. You can do the same math with the binary system. The thing about quantum binary system is in a classical computer, it's either on or off. The coin is either in San Francisco or it's in New York. But a quantum system can be in the state 0 and 1, and that makes all the difference in computing speed for a certain class of problems. Okay, some things we have learned. Quantum physics describes the wave-particle behavior of the atomic world. Electrons, photons, etc. behave both as particles or waves, depending upon what you're measuring. We can't predict individual particle behavior with certainty, only the average outcome. Electrons in atoms exist in probability clouds with discrete energies. They can jump from one place to another without going in between. Quantum objects can be in a state where many different outcomes are represented, such as being in New York and San Francisco, each with his own probability. The act of measuring a quantum state resets the state from many possible outcomes to one particular outcome. So, if you're confused, this is a quote from one of my favorite physicists, Richard Feynman. Feynman won the Nobel Prize in Physics. He also worked at Los Alamos during World War II and has written a number of amusing books, one of which, Surely You're Joking, Mr. Feynman. He used to sneak into top secret places, and he learned how to roll the tumblers on a safe. He would open it up and leave a note inside that said, "Guess who?" Well, he also figured out the frozen O-ring problem on the Space Shuttle Challenger disaster 2 years before his death in 1988. What Feynman actually meant when he said, "Nobody understands quantum mechanics," he understood it better than most people on the planet. But what he really meant, and these are my words, quantum world is very unlike our everyday experience. Therefore, we have to adapt a totally different way of thinking. Even today, it still stretches our intuition some 90 years after it was founded. Nevertheless, quantum physics is phenomenally precise in predicting every experiment in which it has ever been tested. It has never, ever failed, regardless of the precision. We owe our understanding of all of chemistry and materials to quantum physics. It affects every aspect of modern science and technology. By some estimates, over half of the U.S. gross domestic product is directly traceable to this knowledge. And here are some of the physicists. I've already shown you their pictures. They all won Nobel Prizes. Germany was big in the beginning days of quantum physics, all right? But it's become an international field. As I told you, science is an international endeavor. Now, the closing thing is, how many people now think we're living in good times? How many think maybe not so great?
Terrible times.
How many people think terrible times? Okay, most of you are not going to venture out an opinion. All right, I want you to look at this, because the ones in yellow are quantum physics discoveries, and I want you to look down and see what was going on in the world at the time. In 1903, the Wright brothers' first flight, Einstein's special relativity and the photoelectric effect. A few years later, we had the Model T. Then Rutherford and Bohr delineated the structure of the atom. Something really bad happened. On its maiden voyage, the Titanic went down and 1,200 people drowned. You might think this is good or bad, but in 1913, we adopted the income tax. In 1914, World War I began. It lasted for 3 years. In 1917, the Russian Revolution. Hitler finished Mein Kampf, which in German means my struggle. In 1923, and 1 year later, de Broglie invented the wave-particle relationship. In 1924, Stalin became Soviet dictator. He lasted until 1953. In 1924, Robert Frost won the first of 4 Pulitzer Prizes. Then Wolfgang Pauli invented the Pauli exclusion principle. We can't talk about that, but that's why matter is hard. The Scopes trial in Tennessee. The man Scopes was convicted for teaching evolution in the classroom in 1925. In 26 and 27, 2 big discoveries in quantum physics. 27, Lindbergh flew from New York to Paris. The same year, the Babe Ruth hit 60 home runs. In 1928, the discovery of antimatter, which is directly out of quantum physics, by Dirac. Fleming discovered penicillin that year. 1929, the world was plunged into a worldwide depression when the stock market collapsed in the United States. So, it may not be as bad as you think it is right now. You don't know what's going on behind the scenes. Some of the things that are going on could be changing life dramatically in the future. Thank you very much.